very much indeed, and thank you for coming. Time, unfortunately, is really short, so I'm going to talk mega fast. This picture I call the Ascent of Mallard. And this is the title page for my new book, Unnatural Selection, which is a book all about selective breeding. Now, selective breeding isn't the same as domestication. Domestication is the transformation of wild animals into self-perpetuating populations of tame ones. Selective breeding, on the other hand, is the ongoing process after that, where those same tame animals are then converted into animals which are more productive, more beautiful, more interesting, or just generally different. It's an ongoing process. This is a talk and this is a book about selective breeding on a far, far grander scale, a scale that actually encompasses all life on Earth. But we know it by a different name, there you go, and we call it evolution. Now, a lot of the evolutionary principles I'll be talking about will be familiar to all of you, but maybe not in this context. But this was the context that Charles Darwin himself used to explain how evolution works. Now, this isn't going to be a lesson about evolution, though. This is going to be looking at different preconceptions that we have, different prejudices against domesticated animals, because in general, as naturalists, we don't take them very seriously. We think they're cute, we think they're just for the children, or we might think that they're a terrible travesty and what an awful thing for people to have done to wild animals. I call these people wild animal snobs, and I know all about them because I used to be one. But it hasn't always, it hasn't always been like that. If you'd have opened a bird book around the early 19th century, you'd have seen domesticated breeds listed alongside wild species, even given scientific names. And this wasn't a mistake. Whoopsie, what is going on here? There we are. This wasn't a mistake. This was because PreDarwinian Taxonomy was all about just listing, cataloguing what existed on the planet at any one time. People have always known that animals change. Nobody would have said that animals don't change. People have been selectively breeding and changing and improving livestock ever since the Roman times, and maybe even before. So nobody would say that animals don't change. Well, what we thought was that animals change along a linear, parallel pathway. The modern breeds that we have, the modern pigeon breeds, like the one we just looked at, came from the same types, the same general types from way back in time. An ancestral pouter, an ancestral carrier, and so on. There are so many, there are hundreds and hundreds of different pigeon breeds. And as Darwin pointed out, if you're a taxonomist, given the task of naming them, cataloguing them, you would name them all as different species because they are so incredibly different. All we have to go on is the animals in existence at any one time. It's like looking down over a great vast tree from above. All you can see are the leaves and the tiny twiglets and the tiny little tips of the branches, just the very topmost layer. And you can't see whether those twigs are joined onto bigger twigs and bigger branches and bigger limbs and whole trunks. And if so, you can't see which ones they're joined onto. And this is the problem facing taxonomists of all time. But there are branches. It's not parallel. Linear evolution, it's branching evolution. And all of those domesticated pigeon breeds are all actually descended from one species. All the pigeons you see in the town centres are all from the rock dove. All domesticated pigeons are from the rock dove. They've got a common ancestor. Exactly like, come on, we haven't got much time, there we are. Exactly like Darwin's tree of life. The same process between wild and domesticated animals. Slow today. Animals are plastic things. They change. And whereas it's impossible to see change happening in wild animals, you can't see evolution taking place. In domesticated animals, you can actually see visible change within just a few animal generations. This is the old-fashioned type of garden fantail that we had about the mid-20th century, and by the end of the 20th century, they look like this, modern exhibition fantail. That posture, by the way, doesn't do them any harm. They assume that posture when they're excited. Normally, they're perfectly able to act and behave like any other pigeon. Plastic things. This is, oh, come on. There we are. Going to give away all my surprises like this. Bulldog wretched thing. There we are. Bull terriers around about 1900 started out with a very normal, straight cranium, straight skull. Over time, the muzzle was just rotated downwards a little bit more in every generation until we've got the bull terriers that exist today. There's nothing wrong with them, as far as I know, health-wise, caused by the skull at all. It's just a change. Now, these changes that we can see in domesticated animals through selective breeding weren't lost on Charles Darwin. And if you open The Origin of Species expecting to see wonderful descriptions of adaptations in wild animals, you'd be disappointed, as I was when, as a 16-year-old, I started to read on The Origin of Species, because the first chapter, it's a big chapter too, it's all about pigeons. And I thought, how dull. But Darwin was really clever to make this analogy between how natural selection and selective breeding actually works, because the Victorian public found the idea of natural selection a truly terrifying concept, and I believe in many ways it still is. The idea that all the diversity on the planet could have evolved without the need for a divine creator is a scary concept then and now. So Darwin made it palatable, he made it easy to accept by comparing natural selection and selective breeding. It's like the spoonful of sugar to make the medicine go down. So I've talked quite a lot about natural selection. I know that you all know how it works and what it is, but basically it goes on this premise. It's a lovely, elegant, very simple equation. All individuals are very slightly different. And those differences will be passed on usually from one generation to the next. And then in terms of, in the great struggle for life, when we have competition for life, then some individuals will do better than others. Those differences will actually make them better able to exist and to pass those traits down to the next generation. So looking at it purely as an equation, we've got variation, not just variation, but heritable variation. That's the random part. And then we've got the non-random element, which is selection. Heritable variation plus selection equals evolution. If you take nothing home with you today apart from one thing, let it please be this: survival of the fittest is the most misunderstood, misinterpreted and downright dangerous phrase in the whole of science. So we'll get rid of that. It's nothing to do with survival. You can live 100 years and it doesn't matter if you don't produce any viable offspring. What matters is the following. What matters is reproductive success and being best fitted to your environment. Now, being physically fit is obviously going to be a good thing at an evolutionary level, and that's why the misunderstanding has carried on for so long. But it's nothing to do with being physically fit, it's being best fitted to your environment, and the environment is the most important thing here. Now, here's an example. You're an animal that's just got the sudden trait, inherited the trait to develop a very thick coat, which can be a really good thing at the beginning of an ice age, but it's not such a good thing at the beginning of global warming. It's all about the environment. Okay, so next bit of prejudice here. Domesticated animals are just man-made freaks. Well, looking at this dog skull here, you might actually think that that's entirely true. And of course, nobody would condone the deliberate breeding of animals which are physically suffering or can have a short lifespan. But let's face it, there are some pretty freakish things in nature too. Take sword-billed hummingbirds and sloths, for example. And if people say to me, oh, look what humans have done to toy dogs, I'll say, look what flowers have done to sword-billed hummingbirds. The same traits can and do occur equally in domesticated or in wild animals. There is nothing about the domesticated environment that causes these things to happen. They can happen just as easily, they happen on their own, spontaneously, and they may or may not be favoured by those environments. Now, take naked-necked chickens. You might think naked-necked chickens are rather freakish things, and you might be right. You might prefer chickens with feathers on their neck. But nobody ever complains about naked necks in Nairobi storks and ostriches and so on. In wild birds living in hot climates, having a naked neck can be a very good thing for losing heat through your neck skin. In domesticated animals, well, naked-necked chickens are from Romania. It's not very hot there, but breeders just find them interesting. So it's just a different environment that happens to favour the naked neck trait. Now, on the subject of chickens, this is Peter Baumann. Peter Baumann was a travelling salesman of veterinary products in Iowa around about the 1940s, and he would drive to different farms and sell his stuff, and farmers would bring him in, a cup of tea, and every so often something would come up in conversation. Oh, you want to see this chick that was hatched this morning? It's really weird, it's got no wings. And Peter was a bit of a weirdo, his eyes would light up, and he'd say, oh, would it be okay if I take it home, please? Can I keep it? And the farmer said, yeah, okay, if you want to, And Peter actually built up, by very skillful selective breeding, he built up an entire self-perpetuating flock of totally wingless chickens. Peter Baumann didn't like chicken wings, and he assumed nobody else liked them either. He also thought there was another added advantage to this in that you can see him posing here with his 18-inch high fence. He thought the chickens couldn't actually escape from, if they had no wings. Nobody pointed out to Peter Baumann that the purpose for fencing in poultry is to keep predators out and not to keep the chickens in. Now, wingless chickens is a pretty gross idea, right? Who thinks wingless chickens are a gross idea? I think there's a lot of, I think you all want to put your hand up, really. But on a certain island where there are no mammalian predators, some birds evolved which had absolutely no wings whatsoever. Oh, come on. Sorry, pretend you didn't see those. Oh, wretched thing. A whole group of birds evolved, 9 species of moa, great big things. Now, it may be that moas lost their wings gradually over millions of years of evolution. But not a single fragment of wing bone fossil has ever been found for a moa. So it's equally likely, I'm not suggesting this, but it's possible that moas might just be very, very big wingless chickens. The M word, yes, the M word's very tricky. People get very touchy about the M word. You lose friends when you mention the word mutation. People don't like it at all. Now, they think about things like bearded ladies, two-headed lambs, roll up, mad scientists, white coats, thick glasses, and all sorts of bad things pickled in jars. Now, mutation in the evolutionary sense does not mean monster. Pretend you haven't seen the slide that's coming up now, because that would spoil the surprise. Ladies and gentlemen, monster, I will show you a monster. But some of you with a delicate disposition, or ladies in the audience, might want to close your eyes at this point. There we are. Oh, good. Somebody said, oh, I like it when they do that. Absolutely. Now, things like six-legged puppies and four-legged ducks are not mutations that we mean in the evolutionary sense at all. What we really mean when we're talking about mutations are very, very slight changes, tiny, tiny copying errors in DNA, just the things that you would hardly notice, but might make a difference in an evolutionary sense. Sometimes the steps are bigger than others. This is well, let's see what's wrong with this chicken. You can probably see it better like this. It's got really short legs, but it's also got really short wings too. It's a dwarf, it's a disproportionate dwarf, which means the body is exactly the same and the limbs are shortened. And it's the same, we don't really think of it in birds very much, but it's the same as what happens in these. It also occurs in lots of other animals too. Come on, there we are, there's a cat version. They're really cute. They're called munchkins, and they're very sweet. And if you think it might be a bit cruel to deliberately breed short-legged cats, I've spent a whole day playing with them, and they're gorgeous, and they can run up the curtains as well as the next cat. They don't seem to be affected by it in the slightest. Now, disproportionate dwarfism can and does happen in all sorts of animals. It's happened in elephants and foxes and humans, of course. And who knows, it may have even been favoured at one or other time in evolutionary history to produce things like our mustelids, for example, weasels and stoats and so on. Obviously, there's going to be millions of years of selection reinforcing that, but they may have just got a small leg up from a mutation like that. Now, we talked a lot about being in the right environment to support these traits. Environments come in all different shapes and sizes. When a short-legged sheep was born to a farmer not that the farmer didn't give birth to it, it was born to a sheep, a farmer in Massachusetts. He thought he had the big dollar sign coming up, ding, over his head. Hey, short-legged sheep can't jump fences. And just like Peter Baumann, he deliberately bred an entire flock of short-legged sheep, and he did. He saved a fortune on fence repair. And they became internationally famous all over the world. They even reached the attention of a young Charles Darwin. Now, short-legged sheep might not be able to jump real fences, but they certainly seem to have made an evolutionary leap. And that confused Darwin no end, because he was constantly pointing out the gradual nature of evolution. Natura non facit sortus, he would say. Over and over again, nature does not make leaps. A few years later, Richard Goldschmidt was saying nature has to make leaps. We cannot have the diversity that we have on the planet without nature making some severe leaps. And he had coined what he called the hopeful monster theory, which was met by ridicule. He was saying that the sorts of weird mutations we were talking about earlier were the reason for the diversity we have on the planet now. He was met with ridicule, but it's not quite as crazy as we might think, because some very large evolutionary phenotypic changes in the external appearance of animals, can be brought about by a smallest genetic change, just a small flick of a switch to change the trajectory from one thing to another, and you've got another branch on that evolutionary tree. Nothing can make these mutations happen in the first place. This is an interesting mutation. It might look like a scabby old town pigeon, but this is actually a very early example of a throwback pigeon, a type of pigeon that Darwin would have kept. Nothing can make those feather tips twist the other way. You will never get that in nature. No matter how much you selectively breed pigeons, you will never get that happening. It happens on its own. But once it's happened, then you can select on that. And Darwin, I think, would have been delighted and thrilled to have seen what throwbacks would become in another 150 years. Look at that. Colours, that's another thing that can happen in one single step. This exercise is called Let's Colour a Gordian Finch, and we're going to show some effects of just simple one-step pigment changes. We're going to start with the blank palette. All of these birds can and do occur in real life. Go to a bird show, you'll see all of these different colours. Okay, start off with a blank palette and then add carotenoids. That's the red and yellow pigments. Then you can add eumelanin, that's the blue-black pigment. There we are. So you get does that happen? Does that work? There we are. So you get blues and you get greens too, and blacks. Blue and yellow make green. It's just like adding transparent layers of a watercolour painting or a silkscreen print. Now we'll add the other sort of melanin, which is pheomelanin. That's usually reddish-brown, but when you add it to a certain feather structure in Gordian finches, then it turns out purple, which is rather nice. And this is the wild-type Gordian finch that you have in Australia. And you can remove pigments too. Take away eumelanin, take away carotenoids and pheomelanin, and just one simple step can make big changes. Come on, there we are. Now we've talked about changes in structure, changes in bone length, changes in colour. And you can also have changes in the numbers of bones too. Any textbook will tell you that wild boar has got 19 thoracic vertebrae, but they haven't all. There's a lot of individual variation. And of course, nobody in their right mind would actually select an animal for extra vertebrae or extra ribs. What's the point in that? But they would select an animal for extra meat. Wild boars, of course, are the wild ancestor of all our domesticated pigs. Pigs that get for meat, so you breed from the ones with the lovely long body that give the best meat yield, and inadvertently you're selecting for extra vertebrae. It happens all the time. It's a really very simple process to add on a body segment. It's not like adding on functional limbs. It's just adding on the extra body segment with the ribs and surrounding tissue and so on. And it happens more often than we would realise in nature. Inbreeding, yes, everybody says, oh yeah, they're all inbred. And do forgive the black humour of the web poor, I couldn't think of a better image. It's a criticism commonly thrown at animal breeders that everything's inbred. Well, let's look at that a bit more closely. And to start with, there's an awful lot of inbreeding in nature as well. Nobody ever criticizes inbreeding when we're talking about waifs and strays like Galapagos finches turning up on isolated islands and which are all in bed. Neither would we complain about inbreeding when we're talking about bringing species back from the brink of extinction. Things like Mauritius kestrel brought back from just 7 individuals. Inbreeding can be a really good thing if you combine recessive traits which are not usually seen, put them together, and then you see what's there. You can eliminate those animals from the population and then carry on without them with improved livestock, with improved stock. And that's what Robert Bakewell, our greatest agriculturalist, actually made a practice of doing, breeding in and in, as he called it. And sometimes, just sometimes, inbreeding does no harm at all whatsoever. How many of you have got or have ever had a hamster? Oh, most of you, that's nice. And did you know your hamsters are all related? You can set up a Facebook group. And they're actually all descended from one single pregnant female that was collected in the wild in 1925. And they breed, and they breed, and they breed. And there's absolutely no problem with hamsters. There's no loss of fertility, no loss of fecundity. They just carry on. There are no genetic diseases. And next time somebody's saying, oh, inbreeding's terrible, just think of your hamster. They wouldn't survive in the wild, and that's often, that's a common one too. What people really mean, though, is that they wouldn't survive without man. Is that such a terrible thing? Man's not going anywhere. This is just the ones with electricity. I mean, it's a lot worse than that. I don't think we need to worry about these things surviving or not, because it's just another symbiotic relationship between 2 species. It's a nice, much better way of thinking about it. And to be honest, there will still be short-nosed dogs walking in our parks when all the wolves sadly have gone. Sad but true, and that's still an evolutionary success for Canis lupus. Tameness isn't the same as domestication, but looking at wild animals that have actually got used to being around man. Is this tameness genetic tameness, or is it just learned behavior? Now, one man who thought it was definitely genetic was a man called Dmitry Belyaev, who did an experiment with foxes to prove his theory. And he was one of the scientists who was forced to flee from Russia in Lychenko's persecution and went up to Siberia, where he actually kept this fox farm. He wasn't taming the foxes, he wasn't petting them, he wasn't stroking them. He had completely wild foxes in cages, sort of fur farm environment, and he would choose to breed from the ones that were just chilled when they were fed or were friendly, and the ones that were aggressive or afraid, those are the ones that were taken out of the population. And within a few fox generations, Belyaev actually had all of his foxes friendly, domesticated, pleased to see him, wagging their little tails, and it came with a whole suite of other effects as well, floppy ears and piebald colours and curly tails. This has also led to the idea that maybe humans are actually self-domesticated, and there's a whole suite of what we call pleiotropic effects that sort of come with domestication. Now, we talked earlier about our formula for how natural selection works. Inheritance is the crucial thing. We're not going to talk about that now. You're pleased to know that we're almost out of time. But inheritance was Darwin's sticking point. He didn't know how it worked. He'd already been working on the theory of natural selection for 20 years. And he would have carried on happily for another 20 years to work out where the variation comes from and how things are inherited. But something happened. You'll be able to see on the plaque over here. Alfred Russel Wallace came up with the same theory at the same time and sparked Darwin into action. He responded straight away by producing On the Origin of Species. And he promised to come back with a future book to tackle the question of variation and inheritance. And that book was on the variation of animals and plants under domestication. It's an awful book. It's virtually unreadable. It's a very good compendium of facts about selective breeding, but it's not a very good book. And the worst thing about it is that he didn't actually manage to work out the answer to his riddles. He worked so hard at it, though, gosh. And he wrote to everybody. He picked the brains of every livestock keeper, everybody he could think of from the most aristocratic racehorse owner to the humblest gardener. The one person Darwin actually left out was, sadly, the one who actually had the answers that he sought, a monk working in a monastery garden growing peas in Brno in Czechoslovakia. My book, Unnatural Selection, is intended to be a tribute, a monument to what Darwin may have achieved if things had been very slightly different. I'm going to race through the last bit now. This is the fun bit at the end. But Darwin hated doing his book, and he described it as 4 years and 2 months of hard labour. Mine was 6 years and 2 months. And like Darwin, it involved us going to lots of different farms and small holdings and talking to a lot of different people. Learned all about double muscling in cattle in Belgium, went to lots of different people's pigeon lofts, learned about long-tailed fowl and the different milk strategies. It takes a very special chicken to grow, with the capacity to grow a 27-foot long tail. Had horse skeletons put together for me in New York State, and got to play with lots of lovely munchkin cats and kittens. Oh, come on, don't do this. Lots of boiling of bones as well. There are pictures of whole animals in the book as well, but as with the unfeathered bird, there was lots of boiling at home too, and this time it could be anything from ducks to dachshunds in the cooking pot. Husband does all the boiling and the reassembling of skeletons, and he would be working every weekend downstairs, putting skeletons together in the right posture, the right for the breed, and for the breed in history as well. A really highly skilled job. Not many people could do that. Meanwhile, I'd be upstairs working away on the text and on the pictures. The unfeathered bird has got 385 pictures, and this one has got 425. I'd cross them off on a list upstairs and write it on the wall, and gradually, we got there. I wanted it to be a beautiful book. I'm very proud of the text in this book, but I wanted it to be really beautiful as well. It's like a work of art and science. So once again, I chose to produce the images in a nice sepia colour and to have them printed on beautiful cream-coloured paper. So it's a thing of beauty, even if you don't read it. There's an image also on every single double-page spread. But most importantly, I mean, this wasn't just a book that was written, researched, illustrated, and so on. This wasn't just an academic thing. It's all based on the animals that we keep, and I can't take credit for this. Husband's been keeping selectively breeding birds for his entire life, and not in a way, not for pigeon racing, not for shows, not for exhibition, but for experimental breeding, just like Darwin did. There was not enough time to go to tell you all about these, but he did some wonderful things. The unfeathered bird was, it took 25 years. Husband came along in the final 5 years and did so much work for it that I actually produced Unnatural Selection as a thank you present to him for helping me with the first book, though I think it made him do so much extra work that he was saying, no, don't help me, don't thank me in future, don't thank me, it's okay. Because he worked, like me, tirelessly for 6 years on this book as well. The previous book was dedicated to a dead duck, and you've got to come to one of my other talks to find out why. This one, of course, had to be dedicated to husband, naturally, and some things never change. There he is as a kid, and there he is now, exactly the same. And just in case you're wondering what happened to that four-legged duck we saw earlier, she's still alive and well. She's now in possession of just 2 legs. She's called Quad, and she's a very much loved part of the family. Okay? Thank you very much. Thank you.